Hi, this is the second section of stellar distances. We need to look at absolute and apparent magnitudes. Describe the apparent magnitude scale. In the syllabus it says, students should know that apparent magnitude depends on luminosity and the distance to a star. So it depends how bright the star actually is and how far away it is. They should also know that the magnitude of one star is 100 times brighter than magnitude 6 star. So a difference of 5 magnitudes is 100-fold change of. So it depends on luminosity and the distance. And it means that if you have a very luminous star, but it's a huge distance away, the apparent magnitude will be more because it appears to be very far away. And if it's very dim, if it appears to be dim to us, it's going to have a very high value for its magnitude, and we'll look at that now. Now, you know how bright stars are by looking at them from Earth, and this is all we have to go on, really. And so we describe the stars on how bright they appear to be to us. The Earth we look at the sun, and the sun is very bright. So it has the largest, it's the most brightest thing in the sky. So we have to give it the highest value. Now, the magnitude scale, they order the stars in the sky from the brightest to the faintest. The brightest stars had small magnitudes. Dimmest stars had very large values for the magnitude. So the first magnitude ones were basically the 20 brightest. The second magnitude were the stars less bright than the 20 brightest, and so on. The 6 magnitude stars were ones that you could barely see without a telescope or binoculars. So that's the way it works. So later astronomers quantified this system, did the calculations, and they worked out that this magnitude scale that the Greeks came up with was basically a log system, a log scale. And for every magnitude it corresponds to a factor of 2.5 change in brightness. So if you ever go from a magnitude 2 to magnitude 1, the magnitude 1 star is 2.5 times as bright. It gives out 2.5 times as much energy as far as we're concerned. 5 magnitudes is a factor of 100. So it's basically each magnitude is 2.5 times 5, or to the power of 5 rather, so it's going to be 2.5 to the 5, and that will give basically 100. You try that with your calculators. Now, this is the problem with this, is that the brighter stars have smaller magnitudes. The fainter stars have very large magnitudes. The magnitude of 10 is a very faint star. We can't possibly see it without using a very good telescope. And also on the other side, if you have a very small magnitude, it goes to 0 and then it becomes more negative, then this means it's very bright. The sun has an apparent magnitude of negative 26. It's so bright. The sun has a magnitude of negative 26. The full moon has a negative of negative 12 because it's so bright. The Venus, which is a very bright planet night sky, is negative 4. Sirius, which is the brightest star, is actually negative 1.5. Once the system had been calibrated a bit better. The faintest you can see in an unpolluted place is around 6 to 7. The faintest star, which is visible from Earth telescopes, is roughly a magnitude of 25. So we basically give a number to it to describe how bright it is. For example, Betelgeuse or Betelgeuse, or however it's pronounced, and Rigel have apparent magnitudes of 0.3, 0.9. So Betelgeuse is this one, has a magnitude of 0.3, this one has 0.9. They're both very bright stars. This is why we have such low values for them. Which one appears to be the brightest out of Betelgeuse and Rigel? Well, 0.3 is the smaller value than 0.9, so Betelgeuse is going to be the brighter star. It has a brighter apparent magnitude from our point of view. So knowing how bright the star looks doesn't really tell us about how bright the star actually is. We need to find the luminosity to be able to work out the temperature. So we need to know, if we know the brightness of it, if we want to find out how much it is, we need to know its distance. We need to know how far away it is. Find the distance. Well, we can use parallax to figure out the distance, and then we can figure out the luminosity. Once you have the brightness, the apparent brightness, and the distance, we can what its actual luminosity is, its real brightness. So we put luminosity on the absolute magnitude scale for the magnitude scale. The absolute magnitude is basically a standard way of looking at all stars from a standard distance. So the absolute magnitude is the magnitude an object would have if we put it at 10 parsecs away from the Earth. Or you could say it is the magnitude that the star would have if it were viewed from a distance of 10 parsecs. This is the absolute magnitude. So it's the how bright a star is as measured from the Earth. This is the apparent magnitude. So to standardize all stars, we have to, let's say we're viewing them from 10 parsecs. Each star viewed at from 10 parsecs would give its absolute magnitude. So if the star were 10 parsecs from the Earth, or if the star were viewed at a distance of 10 parsecs. So this absolute magnitude gets rid of the effect of distance. So the Sun has an apparent magnitude of -26, but really it would be 4.4 if viewed from a distance of 10 parsecs. But we're very close to the Sun, so it has a much brighter magnitude than it does than absolute magnitude. Aldebaran is further than 10 parsecs. Its absolute magnitude is brighter than its apparent magnitude. So if it were viewed from 10 parsecs, it would actually be brighter. So the apparent magnitude is plus 0.9, and its absolute magnitude is -0.7. So if it were observed from 10 parsecs, it would actually have be actually brighter, because it's actually further than 10 parsecs from us. So remember that this magnitude scale works backwards. Now, if you know the apparent magnitude, which is small m, and the distance in parsecs, which is d, star's absolute magnitude, which is capital M, you can use the following equation. M minus m is equal to 5 log d over 10. Where do these things come from? D is because we're comparing with 10 parsecs. 5, remember that it's 5 magnitude scales. Remember log because it's a logarithmic scale, and we have to look at the difference between the apparent magnitude and the absolute magnitude. We'll look at an example. This is the apparent magnitude, absolute magnitude, and this is the distance in parsecs. So, for example, find the absolute magnitude of the Sun. We know that the apparent magnitude of the Sun is -26.7, and with the distance of the Sun from the Earth is 1 astronomical unit, which in parsecs is 4.9 times 10 to the -6 parsecs. So we put those values in, and you can try this, and you find out that m, the capital M, the absolute magnitude is roughly 4.8. So here's the equation again. A star of apparent magnitude is 4 is known to have an absolute magnitude of 1. So in other words, if it looked at from 10 parsecs, it would have a 1. It would be very bright. But it's got an apparent magnitude of 4, which makes it much dimmer. So really it must be much further than 10 parsecs away from us. Is it closer then or further away than 10 parsecs? Well, apparently its apparent magnitude is quite dim, so it must be quite far away. Can you calculate the distance to the star? You know the apparent magnitude, you know the absolute magnitude, so you can find out what d is. So we have ways of describing the brightness. Now, if we have it in absolute terms, we can find with its magnitude scale. The absolute magnitude is how bright a star would be if it were viewed from 10 parsecs away. And the appearance from the Earth gives the apparent magnitude. how it appears to be from us. Then if we look at the power output, absolute terms, this is the luminosity. This is the amount of energy a star radiates per second. And the appearance of Earth gives us the brightness. Remember the equation. The brightness is the power divided by the area at where the Earth is.